Okay, so we're going to add a little twist to what we've done before. Simply because we're adding, or we have 3 charges instead of 2. And this is going to be a slightly different than what we're accustomed to as far as adding our vectors. Now, this is nice because it's just in one plane, so we don't have to worry about any angles. But there's 2 things that we need to take into account. We have to give these guys direction, so we need to choose which way is going to be positive and which way is going to be negative. Just customary is positive is to the right, and so the negative would obviously be to the left. So what do I mean by that? So this 48 microcoulomb charge, to the right of it is this 95 microcoulomb charge. So that direction to the right I would call positive. To the left, to the 65, then that would be a negative direction for that vector. And that's all I'm doing there. This just defines for me what direction means what. Now we're going to deal with the positive and negative repulsion here and attraction here. So a positive to a negative, they're opposite charges, they're attractive. So I'm going to call attractive forces positive. So long as you're consistent when you define this up front, your answers will come out correctly. You just need to define at the end what a positive or negative number means. Now the good news is that we do get to use our same force equation. Force equals K, Q1, Q2, QR, Q2 over R squared. And the next thing I'm going to do, just for simplicity, I call these guys, or I name them, so I can kind of keep track. I think the book just labels them what they actually are. It's your choice. That's total personal preference. So, vector A, or force A, so the force equals, and I don't want to carry this K through, so I'm just going to pull it out and make a big equation to go inside. And so now let's talk through what we mean by these two for defining our positive and our negative. I'm going to start with the 65. I'm going to move to the right, so directionally that's a positive vector. So far we're not changing sign. And that R squared, I guess it would be ever so helpful if I told you what that distance is. 0.35 meters, and this is also 0.35 meters. So the bottom, that's easy. Let's go ahead and do that. 0.3, not 2. 0.35 meters squared. And the top one now, these 65 coulombs. 65 times 10 to the negative 3. I'm sorry, 10 to the negative 6 coulombs times this 48 coulombs. 48 times 10 to the negative 6 coulombs. Now, what is this going to be? Is this a positive or a negative direction or attraction? We're a positive to a positive, therefore it's negative. It defined anything that's not attractive as being negative, so it's negative. Let's move on to the next one. Our 65 to our 95. This is again to the right, so we'll stick with the plus sign. And start with our 65 times 10 to the negative 6 coulombs times 95 times 10 to the negative 6 coulombs. Now that distance has grown. It's twice what it was before, so 0.70 meters squared for our R. Now, is this attractive or repulsive? I have a positive to a negative. It's attractive, so that sign's not changing. So now we'll button push. Let's see what we get. We get K times. Okay, so I get negative 1.287 times 10 to the negative 8 coulombs squared per meter squared. Now I'm going to multiply it by K, which is this 9.0 times 10 to the negative 9th. and I'm going to get negative 115.81 newtons is the net force for point A, or charge A. So actually, let's denote that a little nicer. So the force on charge A is experiencing from the other two is this negative 115. So now my negative actually means something, because I've defined what an attractive force is by sign. So it's not a positive, it's a negative. It's a negative repulsive force. So apparently this attractive force to the 95 isn't enough to override this repulsive force of 48 at the closer distance. So let's see what happens with our point B. So our point B, force equals K times, okay, so we're going to the left, that's a negative, and let's write in these two charges. Actually, let's just write in the distance. So the 0.35 meters squared. And what's going on up top, we have our 65 times 10 to the negative 6 coulombs, and our 48 times 10 to the negative 6 coulombs. Oops, forgot my units. Now, this is to the left and it's repulsive, so I'll end up with a negative times a negative. So to the left is negative and repulsive negative, which is going to make this guy a positive overall. And we're going to talk about why that actually makes sense. Put in my plus sign. We can change it if we need to. To the right is the 0.35. That's positive, so we don't need to worry about that. 0.35 meters. And that quantity squared. So to the right we are starting off with our 48 times 10 to the negative 6 coulombs, and multiplying it by this 95 times 10 to the negative 6 coulombs. Now this is an attractive force, so it's to the right, it's positive, and it's attractive, so it's also positive, so that positive stays. And so let's talk about why that makes sense. What's going on here? This is like a tug of war. So this guy, this charge is repulsing this charge. Well, if it's being repulsed, then overall its net direction is going to push it this way. And this negative charge is attracting this charge, also pulling it this way. So overall our forces should be adding up, they should be increasing, because it's getting a push from behind and a pull towards it. So everything is going in that direction. So this actually makes complete sense. And the peanut gallery needs to go have another piece of pizza. Okay, let me button push. Okay, and I get that the sum of these two pieces is 6.269 times 10 to the negative 8. Oh, make sure you can see. Times 10 to the negative 8. And what are our units here? We are coulomb squared per meter squared. Multiply that by K, and our force for B is 564.25 newtons. So 48, realistically we should only have 2 sig figs, but because nothing seems to be consistent with that, if you gave me this many, that would be fine. So our overall force is attractive, and it's to the right. So that's kind of what we talked through for that making sense. So let's do our last one. Last one, C. It's force equals K times, so everything is going to be in the negative direction here. Let's just go ahead and start that off with the negative sign. Make sure you can see. So 95 times 10 to the negative 6 coulombs. times, let's start with this first point, our first charge, the 48 times 10 to the negative 6 coulombs, yeah, coulombs, not microcoulombs, and divided by this 0.35 meters squared. Oops, it's not squared yet. Squared. Okay, so we have that. This is for being in the negative direction. Let me pull this back down. And the force between this negative and positive is attractive, so that's positive. So this is going to stay negative. So what happens to the next one? We'll just put in the plus sign for now. Actually, no, because everything is to the left. So we'll start off with the negative sign. That's accounting for the direction change. And now we are at the full 0.7 meters away. So 0.70 meters squared. And again, we're at the 95 times 10 to the negative 6 coulombs times now our 65 microcoulomb charge times 10 to the negative 6 coulombs. Okay, and negative to positive, so this too is attractive to the left, so it's also a negative charge. Bring it up so you can see it. And that should make sense. I have a negative charge in these 95s. Everything's going to the left of it, but they're both positive charges. So I have two forces acting on it, pulling in the same direction. So I would expect that to increase the strength of the overall charge, not decrease it. I'm sorry, overall force, not decrease it. And these negative signs then are going to mean that that net force is going to be to the left. That's all that means. So let's see what the calculator says. Okay, so I get my forces K times 4.983 times, oops, don't forget my negative sign, times 10 to the negative 8 coulombs squared per meter squared. So K is going to cancel, or the units for that's going to cancel out, will be left in units of force, and our final answer here will be negative, make sure you can see, negative 448.4 newtons. So our resultant force for C, it's experiencing a total pull of negative 448 newtons to the left. So what does this tell us about anything? Let's see if we can't see it all in one spot. So two positive or two attractive forces on this negative charge don't have the same magnitude as being pushed and pulled simultaneously. So remember, this 48 is being pushed by the 65 and attracted by the 95. So it ends up with the net magnitude going that way. But that over r squared thing, everything is only 0.35 meters. We come down here, everything is pulling in one direction, but that second piece is diminished because that 1 over r squared rule. So it's that distance away has diminished how much of an impact those two attractive forces have, and overall it experiences less of a force than our middle charge does. It's pretty cool. We can look up here, and this is experiencing overall a negative charge, or negative, net force to the left. So overall it's being repulsed, so everything is pushing it this way. This is an overall attractive force to the right. This is an overall negative to the left. So hopefully you can see that, and that makes a little more sense. We'll do a little bit more of it, obviously, as we go along.